Welcome to the course on Introduction to Electrical Engineering. We will have a lecture 36 today on 3-phase induction motor part 2. As far as outline is concerned for today presentation is, we will discuss about torque speed characteristic, then the determination of motor equivalent circuit parameters, we will talk about the starting methods of induction motors, then speed control of induction motor and selection of induction motor various applications, followed by numerical problems and references. So, now little bit revision of induction motor equivalent circuit, which we discussed in the last lecture. So, revision of this equivalent circuit concept is here. So, first is we call it rotor winding is open. So, rotor will not rotate, and this is the equivalent circuit as we discussed last time, similar to the transformer, that we have a per phase, this equivalent circuit on the per phase, because we consider all the 3 phase are symmetrical nature. So, we can go per phase basis equivalent circuit. So, starting from input supply, we have a R1 stator resistance, X1 stator leakage reactance, then we will have the shunt branch parameter like representing the core loss by RC and XM magnetizing reactance similar to transformer, then followed by we have a equivalent like a transformer, but here we have a air gap through which the voltage is induced from stator voltage to the rotor voltage, and typically the of course, if it is under block rotor condition, that as the rotor is not rotating, then the same frequency is the voltage similar to transformer, and of course, we have a resistance and leakage reactance of the transformer at the same typically at stator frequency like and all these parameters are defined here like. So, now this equivalent circuit, of course, we can say when rotor winding is shorted, it is a normal condition. Now, the induced voltage will not be corresponding to that one, it will be slip times the the slip times the induced voltage, slip times the voltage induced at under block rotor condition, and then of course, we will have a resistance also changing, as well as you will have not resistance will be the same, but the reactance will be a function of now slip frequency. And then coming to step 3, we have to now eliminate the typically the frequency F2, or you can call it SF. So, then we have to bring entire equivalent circuit typically like here of F1 and on the rotor side F2. So, this is the equivalent circuit, and you can find out the when the rotor current typically keeping the same. So, we are able to divide by S, this whole current will remain the same, but this S we can divide it by numerator and denominator. So, that will be corresponding to the same current, and then the equivalent circuit can be transferred to stator side, because we can transfer the your rotor resistance. Now, it is R2 dash, because it is a turns ratio square as it is shown X2 dash square A square X2 and R2 dash equal to A square R2, where and I2 dash will be I2 upon A, and where we can call it the it is A effective with the effective turns ratio. It does not include only the turns, but it also includes the winding factors of the stator winding as well as the rotor winding. Because winding factors includes the how the winding is distributed on stator side and rotor side. So, this is the now we can call it is the exact equivalent circuit, this is shown here, and it is at the same frequency of the stator, and we have a resistance of stator, leakage reactance of stator, and then the shunt branch parameter, which represents the you can call it the core loss as well as the excitation current I m, and net current total current is I 0, that is we call it no load current. Then on the other side, after the air gap, we have a current flowing I 2, that is a rotor current, of course, referred to entire to stator, followed by rotor resistance representing the losses in the rotor, and then X 2 dash, that is the leakage reactance of the rotor, and then there is a resistance R 2 dash 1 minus S upon S. This represents the mechanical power output, or the resistance corresponding to the mechanical power output, because that is active power representation here in electrical equivalent circuit on the of the shaft power. Now, of course, there are different circuits. So, IEEE have recommended this equivalent circuit by typically neglecting the you can call core loss here. So, remaining parameter remain there like, and then of course, the revision of this equivalent circuit is in a sense that shunt branch can be taken at the place where we are considering earlier, that R1 X1 and JX1 and JX2 and R2 by S and XM. And now, you can have a Thevenin equivalent across A and B, considering that the entire equivalent circuit we want on rotor current. So, by taking a Thevenin equivalent of it. Of course, you can take even a core loss also into account. So, this V Thevenin will be V phi equal to Z x m upon R 1 plus J x 1 plus x m, and R t h plus J t x will be R 1 plus J x 1 in parallel of J x m. So, we get a Thevenin equivalent voltage as well as impedance, and now where the Thevenin voltage is your supply voltage per phase x m upon under root R 1 square plus x 1 plus x m square. That is the magnitude of the voltage. This is the virtually you can call it with respect to the kind of phase you have considered like. Now, from here we can consider x m is much larger than x 1 and x m is very large than R 1. So, we can say V t h will be approximately V phi x m upon x 1 plus x m, and if x m is also very large than x 1 and x m plus x 1 is greater than R 1. So, we can say R t h will be approximately R 1 x m upon x 1 plus x m, or we can say x t h will be equal to very close to x 1. So, now we can find out the total current in the circuit is only I 2, that is V t h by Z t, and Z t is now R t h plus R 2 by S square plus x t h plus x 2 square. So, then the power converted to mechanical output will be P converted 3 I 2 square R 2 1 minus upon 1 minus S upon S, and the internal mechanical torque or developed, you can call it internal mechanical torque or developed torque will be T in P, that is the P, you can call it converted after the losses in the rotor divided by omega m. So, this will be P converter 1 minus S into omega S, or 3 I 2 square R 2 by S into omega S, or P A G divided by omega S. That is how it represents the torque finally after cancelling all the term here. So, now you can call it this torque, I mean internal torque can be defined 3 by omega S for 3 phase V t h divided by under root R t h plus R 2 by S square plus x t h plus x 2 square, whole square of that, that is R 2 square into R 2 by S, and that finally gets simplified into T internal will be 1 upon omega S into 3 V t h square R 2 by S divided by R t h plus R 2 by S square plus x t h plus x 2 square. And this torque, if really from this you plot the entire characteristic with respect to the slip, here slip is 1, that is the starting, and this is the range for the braking. I mean slip more than 1 means the motor is rotating, this machine is rotating reverse direction, that is the braking, and then this is the unstable motoring, then of course goes to starting, and that is the peak torque, we call it maximum torque, peak torque, breakdown torque, many names are there here, and this is the slip corresponding to maximum torque. Then this is the again the kind of rated torque and slip for rated torque, and then it is a generating region. So, this is the synchronous speed at which the torque developed by induction machine is 0, because there is no induced EMF in the conductor, because of there is no relative motion between the rotating magnetic field and the rotor bar or rotor conductor. So, no induced EMF, no current at synchronous speed, but above synchronous speed of course, I mean it changes and you get the again the generating region, stable and unstable generating region. So, that is above synchronous speed, the slip minus 1 equal to, it means double the typically synchronous speed. So, that we call it generating region. So, that is the typical torque speed characteristic of induction motor, representing this expression between torque and slip. So, here is only the slip is the only variable, the remaining parameters are constant for a given motor as well as for given voltage and frequency of operation. So, now you can say maximum torque occurs with the power transferred to R by S is maximum, and this condition occurs when R 2 by S equal to magnitude of impedance R t h plus J s t x. So, you can take derivative with respect to S, and R 2 by T max will be under root R t h square plus x t h plus x 2 square, and S t max will be R 2 upon under root R t h square plus x t h plus x 2 square, and the corresponding maximum torque of this is T max is 1 upon 2 omega s and 3 V t h square upon R t h plus under root R t h square plus x t h plus x 2 square. So, this torque expression is independent of rotor resistance. So, slip at maximum torque is directly proportional to the rotor resistance. The maximum torque is independent of R 2 and the value of maximum torque remains unaffected. The speed at which it occurs can be controlled by varying the rotor resistance like. And this is the typically the characteristic for different rotor resistances. This is the original rotor resistance, but if you start putting additional rotor resistances into the circuit, then you can say, I mean the characteristic get peak torque gets shifted, but the value of the peak torque will not shift, and you can keep such a high rotor resistance also that the peak torque can be brought to the starting condition also. Now, coming to the of course, the power flow which we discussed earlier also, that we have input power which goes from the supply, then we have a power to stator, we have a stator copper losses, then we have a core losses, this is representing 3 Vrm square upon Rc, the 3 Is square Rs, then it is the air gap power after followed by then rotor copper losses, and then we have a this is, you can call it the power which is going to be out of after copper losses, and then we have friction windage losses followed by this is the shaft power. So, finally, you will have a shaft power here in this diagram like. So, now you can just see here how it is like a, this we call it air gap power, and this is we call it rotor copper losses, and this is we call it the, you can call it the power, mechanical power output or so. So, air gap and typically rotor copper losses, and we call it like a mechanical power output like. Now, coming to torque speed characteristic, I mean the depending upon the various design features, the torque speed characteristic of the induction motor can be modified to suit particular application, and motor designer can modify the shape of the torque speed characteristic by changing various aspects of the machine design, such as cross section and depth of the rotor conductor. So, you can see there are different torque speed characteristics. I mean, one, the peak torque is here, another is this kind of characteristic, another is this kind of characteristic. So, it means by modifying the your rotor bar and shape, you can change this characteristic, that is requirement of application. So, coming to rotor core design, so modification in the design of squirrel cage motors permit a certain amount of control of starting current and the torque speed characteristic, and these design have been categorized by NEMA in standard MG 1.16 into 4 category. Normal torque characteristic, that we call it normal starting current motors design A, normal torque and low starting current motor design B, and high torque low starting current double wound rotor motor design C, and high slip motors design C. And that is what we really call about this NEMA type of rotor. So, power range is normally 0.5 HP to 500 HP, starting current is 6 to 10 times the full load current, and good running efficiency is 87 to 89%, and good power factor is 87% to 89%, and low rated slip is 3% to 5%, and starting torque is about 150% of full load torque, and maximum torque is over 200%, but less than 225% of full load, and typical application is the constant speed application, where the high starting torque is not needed and a high starting torque is tolerated. So, now coming to NEMA torque type rotor B, the power range again of the same, all the things are same, I mean here, but we have a now the narrow rotor bar, deep and rotor bar, and starting current is only 5 times full load the torque. Motor allow the full load is starting, and starting torque, slip and frequency is the same as the design A motor, and this is now design C, that is normally 3 to 200 horsepower type C. I mean, and here we have a double layer, you can call it double layer or double cage squirrel cage winding, and combines high starting torque with the low starting current, and 2 winding are applied in the rotor as the outer winding having a higher resistance and low reactance, and inner winding have a low resistance and high reactance, and operation in such reactance decrease the rotor frequency with the decrease in speed. And similarly, we have a type C on starting a much large induced current flow into the outer winding than the inner winding, and because of the low rotor speed, the inner winding reactance is quite high. So, as the rotor speed increases, the reactance of the inner winding drops, and combined with the low inner winding resistance permits the major portion of rotor current to appear in the inner winding, and typical application is constant speed load requiring fairly high starting torque with low starting current. And type D produce very high starting torque, approximately 275% of full load torque. It has a high starting current, high slip of 17 to 16% at full load slip. Certainly, efficiency is to be sacrificed, and torque changes with the load, and typical application used in higher inertia load. And these are the typical characteristic of different A type, B type, C type, D type, E type, and here it is a most common B type, where you can say maximum torque is up to around 300%, starting current is a 6 times to 7 times rated current, slip is around 0.5 to 5%, and of course, efficiency is medium to high. So, these are of course, other motors also. So, you can see how it is double cage motor look like. So, you have a deep bar, this characteristic for deep bar, this for high bar, and the net characteristic is virtually this characteristic low rotor, and this is the total high rotor. So, these are the how it is going to be characteristic modified by deep bar construction, and this is the double cage construction. Upper having a small cross section, inner is the more cross section area. This is the torque speed characteristic. So, this is for inner cage, this is for outer cage, and net characteristic is there. So, you can say double cage how equivalent circuit is also modified, and then you can have a calculation corresponding to this same way for calculating the typically for 2 rotors and the final characteristic too. Now, coming to the determination of motor equivalent circuit parameters. So, we can call it due to similarity between the induction motor equivalent circuit and the transformer equivalent circuit. Same tests are used to determine the value of motor parameters. So, first is we do DC test, determine the stator resistance R1, and then we do no load test, determine the rotational losses and magnetizing current, similar to the no load test in transformer. And we also call, of course, light running test. In no load test, we also call light running test also. Another is the logged rotor test, determine the rotor and stator impedance, similar to the short circuit test in transformer. And of course, we have a synchronous speed test, that is S equal to 0. So, coming to first test, we call it DC test. So, you can have the purpose of DC test is to determine the resistance R1 of the winding, as you can see, of 3 phase star connected, and variable voltage DC voltage source is connected between the two stator terminals. So, DC source is adjusted to provide the approximately rated stator current, and the resistance between the two stator DC is determined from the voltmeter ammeter reading as you come. You just have here, and you will get the resistance of course, the two windings, which of course, per phase will be half of that. So, since it is DC, so you voltmeter, ammeter, MF, and enough to get the value of resistance, and this is the current limiting resistance, because you might have a source which is itself of quite high nature. So, because of the current is DC, there is no induced voltage in the rotor circuit. So, no resulting current flow, and also the reactance of the motor is 0, the direct current. Therefore, the only quantity limiting current flow the motor is a stator resistance, and that resistance can be determined. The current in the stator winding is adjusted to the rated value in an attempt to heat the winding to same temperature. So, that they will be during normal operation. Winding resistance is a function of temperature. So, then you can call it like RDC is VDC upon RD, and R1 will be RDC by 2, and in case of delta connected, this resistance will be your R1 will be 3 by 2 RDC, because that two resistance will come in series in parallel of another R1 in case of delta connected. So, now coming to the second test, that we call it no load test, or also we call light running test of this induction motor, and that we have a voltage measurement as well as 2 watt meter to measure the 3 phase power, and 3 ammeter of course, to conduct the no load test. Of course, you can have even a typically 1 ammeter out of 3, because if it is a balanced circuit, the motor is allowed to spin freely, and the only load on the motor is a friction windage losses. So, all P converter is consumed by the mechanical losses. So, the slip is very small. The motor is supposed to run almost at synchronous speed. So, at this small slip, maybe 0.001 or 0.1% or less. So, we can say this R2 by 1 minus S upon S will be much greater than R2, or you can call it R2 1 minus S upon S will be much greater than X2. So, we can consider it the equivalent circuit reduces to almost like a open circuit from this side, very small friction windage, like typically shown here, and this we can call it like this is very, you can call it R friction windage is much larger than Xm. So, we can say at the no load condition, the input measured power must be losses in the motor, and P loss PRL rotor couple loss is negligible, because I2 is extremely small, because R2 by 1 minus S upon S is very large. The input power will be P input, PSL, P core plus Pfn A. So, we can call it this is 3 I1 square R1 plus P rotational losses, and where we can call PSL is 3 I1 square R1, and P rotational will be P core plus P friction windage losses. And the equivalent circuit of impedance is Z equivalent V phi upon I1 NL, and that will give you like a typically X1 plus Xm approximately. So, X1 can be found, and in some other fashion magnetizing inductance will be known. So, now coming to block rotor test. So, in this test the rotor is of course, no load test we normally prefer to do at rated voltage, and block rotor test we conduct at rated current to get the your block rotor you can call it the full load copper losses or winding losses. So, in this test the rotor is locked or blocked, so that it cannot move. A voltage applied in the motor and the resulting voltage, current and power are measured. So, you need the adjustable voltage, because you require very small voltage to get the rated current under block rotor condition, because normally the starting current is very high. So, if it is starting current is 5 times the rated, means you have to apply only 20% of the rated voltage to get the rated current, in that case. So, now this equivalent circuit comes in this fashion. So, it becomes R2, and this R2 you can call it like this impedance is very low compared to Xm, and RC is also very high compared to this. So, we can neglect RC and XM here shunt branch parameters. So, this equivalent circuit we can call it like comes out in this manner. So, AC voltage applied to stator is adjusted, so that current flow is approximately full load value, and log rotor power factor can be find out Pf equal to cos phi, cos theta equal to P input under root VLIL, and the magnitude of the impedance will be ZLR equal to V upon I, and from ZLR we can call it all LR plus JXLR. That will be really ILR is R1 plus R2 dash, and XLR equal to X1 dash plus X2, and X1 and X2 are the stator and rotor leakage reactance at the test frequency, and R2 dash will be RLR minus R1, XLR will be evaporated upon F test into XLR, and that will be X1 plus X2. So, you can call it XLR is evaporated upon F test XLR if you are conducting corresponding to other frequency. So, that will be X1 plus X2. So, unfortunately, there is no simple way to separate the contribution of stator and rotor reactance from each other. So, over the years experience has shown that the motor of certain design types have a certain property, and the rotor and stator reactance normally are supposed to be considered equal like. So, this is something like we can call it that in all cases we consider X1 equal to X2, and dividing 4 different type of motors itself in block rotor test. Now, coming to the synchronous speed test. Synchronous speed test, in this test the induction motor is driven at a synchronous speed by external means, and therefore, slip equal to 0. In this case, power dissipation just overcomes friction windage opposition, that is mechanical losses, and S equal to 1, the current flow in the rotor is 0 from the principle of operation of induction motor. So, power transform exactly equal to the core loss flux core loss. So, starting method of this coming to now induction motor. So, we have a different kind of starter. This is direct online automated starter that you can start directly and apply the full voltage, or we have auto transformer type of starter, and then star delta starter. For first motor goes in star, so that the voltage is reduced by 1 by root 3 to the stator winding, and the current is also reduced 1 by third at the starting, and once motor goes to reasonably speed, then we connect to delta, because by that time current is already reduced, and that entire process goes to automated manner nowadays. Earlier we were doing manually, but now it is a different time operated process that we consider, or speed operated, but normally speed operated change over from star to delta is tedious. So, we do the time rated, after certain times we convert it from star to delta, because finally motor is remain to connected or design is already designed in delta connected motor. So, these all starter is used for the purpose of typically reducing the starting current like, and nowadays we have application of variable frequency drive, and from fractional kilowatt to kilowatt range. One of the typical application is the water pumping, and as you can see it even with the submersible water pumps, motors and pump is here, and then you have a solar panel, and you have a typically the drive here. So, now the starting method of Induction to medium voltage medium power drive, that is 6.6 kV to 11 kV, and megawatt range, usually multi-level inverter based drive are used, and the purpose of this drive of we convert AC normal sine wave power to virtually variable frequency to be applied to the motor with the help of solid state devices, that we call it the drive, and so that you can change the frequency as well as the voltage across the motor to get a speed control and efficient operation of to suit the specific application requirement. So, this we call it the drive, virtually available from different manufacturers like IBB, Siemens, Toshiba, Mitsubishi. So, there are plenty of drive manufacturers which you will find Delta developing the drive variable frequency drive for these motors, and certainly many industries use them because they are able to precisely maintain the requirement of the load characteristic with the help of variable speed drive. So, now coming to starting methods of it. In many cases induction motor can be started by simply connecting them to power line. However, there are sometimes good reason for not to doing so. For example, the starting current required may cause such a dip in the power network voltage that across the line starting is not acceptable for rating more than a particular reading, and for wound rotor induction motor starting can be achieved at relatively low starting by inserting extra resistance in the rotor circuit during starting, and this extra resistance not only increases the starting torque, but also reduces the starting current. And typical example here, at the time of starting the motor slip very unity. So, the resistance with reference equivalent will be R 2 dash 1 upon S minus 1 will be 0. So, now starting torque will be 3 T s equal to 3 by s I s square R 2, and at full load it will be 3 by omega s I f l R s upon S f l, with approximation, because starting we apply very less voltage around 20 to 30% for even for rated current, and in that case certainly even if we have a 5 times the current, then drop in the impedance is quite high. So, in all our starting calculation we certainly take assumptions that the shunt parameters are not considered. So, starting current torque can be expressed as T s upon T f l equal to I s upon I f l into S f l, and this is the of course a starting method for slipping motor. We connect the external rotor resistance that increases the starting torque as well as reduces the starting current, because you are increasing the impedance from the whole equivalent circuit in from the rotor side, and these are typically people have used like even the different kind of methods for even for limiting the current for wound rotor induction motor. That is how the current is limited for during starting. So, for cage induction motor the starting current can vary widely depending upon the primarily on the motor rated power and on the effective rotor resistance at starting condition. And to estimate the rotor current at starting condition, all cage motors have now starting code letter, not to confuse with the design class letter on their nameplate. The code letter sets limit on the amount of current that motor can draw at starting condition according to standard like an EMA. And to determine the starting current for an induction motor, read the rated voltage, horsepower and code letter from its nameplate. Then the starting apparent power from the motor can be S apparent, that is rated power into code on the letter. And these are the typically you can call it like how it is, you can call it the designated letters are there corresponding to different rating kVA per horsepower, like that to as the starting is rated horsepower into the code of letter corresponding to this, like. So, now coming to this direct online starter, as you see the typical diagram. So, squirrel cage induction motor are frequently started by connecting them directly across the supply, and suitable for low power low rating motors, starting current of the order of 5 to 10% of the full load current, and typically the current drawn by the motor when starting is excessive because of lack of counter EMF at the extent of starting. So, you can call it direct online starting when cage motor is started direct online. We can say I s equal to V upon Z s c, and starting current equals to short circuit current. So, let the I s equal to 5 times I f l. So, S f l equal to 0.04, that is full load slip of 4%. From this we can find out T s upon T f l equal to I s upon I f l square into S f l, and putting the value then T s upon T f l 5 square into 0.04 equal to 1. So, you can call it starting is the full load torque, but you are going to draw 5 times the rated current at the time of starting. So, it depends on full load slip as well as it depends like how much really the starting current is there. So, you will get torque corresponding to that. So, another is the auto transformer type of starter. So, with auto transformer starter what we do, we first apply the reduced voltage across the motor, and after that we go to the directly into delta connected mode. So, auto transformer starting a tab 3 phase auto transformer to provide the reduced voltage starting, and various windings of the transformers are added to and taken away from the motor circuit to provide the reduced voltage when starting. So, the auto transformer starting is virtually to reduce voltage used for reducing the voltage for starting, which can be obtained through 3 phase auto transformer, and if the voltage is reduced as a fraction of x of rated voltage, then the motor starting initially I c equal to x I s c and I s c, where I s c is equal to starting current, typically line current with full voltage. Then the current drawn from the supply will be I s c line equal to x into x I s c, that is x square I s c, and starting oblique full load torque will be your T s upon T f l x square I s c upon I f l square into S f l. So, torque is also reduced accordingly, like, and this is typically how you can call it like a your auto transformer starting, like of different kind of connections method for, and this is typically your star delta starting. So, first we connect the motor in star, then we go to delta. In star connection, the voltage across the winding reduces 1 by root 3 and current drawn from the supply reduces to 1 by 3. In delta, when we connect finally, so voltage across the phase winding increases root 3 and current of course phase remain root 3 times, but the line current increases further root 3 times because of this star to delta conversion. So, it means in starting current is 1/3, like, and torque is also reduced to 1/3 here. So, because the it is proportional to voltage square. So, voltage reduced to 1 by root 3, but torque will reduce to 1 by root 3 square, that is 1 by 3. So, a star connected motor has a 2 power line connected across the 2 sets of winding, here, and that is how the voltage are there, and delta connected motor has each coil winding directly across the winding of 208. So, this is the method how first we do. First sequence we have close 1, that is supply connected to motor winding, and typically the open one main motor is running, and initially then the close 2. Motor goes first by closing the 1, it goes to type typically, the manner how it is going to be like a typically first by operating 2 in go start, then finally if you really go to into delta, that is the method how go to start delta starting. So, start delta starting, the start delta starting is an inexpensive 2-step method of induction motor starting. So, start delta starting reduces the starting torque to 1/3, that total direct delta starting, and also the starting line current is 1/3 in direct delta starting. So, starting current is ISC equal to V upon ZSC and V equal to line voltage, and starting current is reduced to starting current typically in delta √3 ISC. So, in case of star starting, the starting current is like ISC equal to 1 by V by √3 into ZSC, that is 1 by √3 ISC. So, you can call it I star to I delta will be 1 by 3, and using this we can call it T star upon TFL will be 1 by 3 ISC upon IFL square into SFL, where ISC is starting phase current of delta and IFL is the full load phase current in delta. And this is typically the method of start delta, how this relay contactor analyze and how the starting take place. So, first you will be having a starting here, closing, and that gives the interlocking of it. Then first you connect the line with the one contactor, another you connect in star, and once it comes to, then with the time delay relay you energize typically that contactor which opens the star and connect into delta, and then whenever you want to stop, you can stop it because this coil get de-energized and you will be both the contactor will become offline, will be disconnected from that. So, this is normally nowadays we have a automatic start delta starter like. Well, now another method of starting by reduced voltage. So, we take here back to back thyristor to reduce the voltage during starting, and this reduces solicitor to ramp the voltage, reduces the induced current, minimize the starting torque, and it smoothen the acceleration. So, this we call it the soft starting method. Typically for this back to back thyristor we can control the voltage applied to the stator winding. So, now coming to speed control of these induction motor, for many applications we require speed control. So, we have two motors like a squirrel cage type, another is wound field. The wound field normally we keep a rotor resistance control or voltage injection in the rotor circuit, but squirrel cage we have either pole changing or we control the voltage and frequency like So, these are the method for speed control. So, now coming to pole changing method, speed control of induction motor can be achieved by changing the synchronous speed, and synchronous speed of the motor can be changed by changing the number of stator poles, of course in discrete because number of poles should be even. So, stator winding are designed such that the simple change in coil connection can change the number of poles, and this method requires same number of poles on the rotor. Therefore, it is suitable for only for squirrel cage rotor. So, with two independent sets of stator winding each arranged for pole changing, 4 synchronous speed can be obtained for in a squirrel cage induction motor, and these are typical example that you can have a the connection to change, so that the number of poles are reduced to half or double like, and these are how the winding connections are made with the consequent pole changing, and these are the typical method for how you really can change the winding connection and change the number of poles like from stator side itself. So, there are 4 method, consequent pole and typically the pole amplitude modulation and phase mixing technique for that. Of course, as you can see the characteristic with different kind of pole changing method. Of course, these are not very popular nowadays because we have other method, better method for control. So, another method is stator voltage control. This is stator voltage control. Speed of induction motor can be controlled by varying the amplitude of stator voltage, because that can change the slip of the motor in the speed expression, that is NR equal to 1 minus S into NS. So, here the slip is controlled by changing the voltage, and internal torque developed by induction motor is proportional to square of the voltage. The variation of speed can be achieved by varying the stator voltage as shown in the torque speed characteristic, and this method of speed control commonly employed with this small squirrel cage induction motor driving fan blower, where the cost is not an issue and the inefficiency of high slip operation can be tolerated. So, you can just see how the speed control is there. So, as you reduce the voltage, you will get the speed reduction here. Of course, you can have a characteristic with high rotor resistance, then you will get this method more effective for speed control. Now, another method is typically voltage and frequency control. So, when you change the frequency, of course, the synchronous speed is changed, and this method considered one of the best method for speed control by variable frequency drive. Nowadays, we have solid state drive for that purpose. Anyway, you can have a regeneration in many applications like railway and metros, all we are having now this your variable frequency induction motor drive. So, synchronous motor of synchronous speed of induction motor can be changed by varying the frequency of stator voltage, and the frequency of stator voltage can be changed using a very small electronic frequency changer, and as the flux density had to be maintained approximately constant, the stator voltage should also be very proportional to frequency, and this is known as a constant voltage to Hertz or V by F control, and the frequency change is mostly used in voltage source inverter, current source inverter, and cycle converter and matrix converter. So, coming to from Faraday law, the air gap component of the armature voltage in AC machine is proportional to the peak flux density in the machine and electrical frequency. Thus, the neglecting the voltage across the armature or stator resistance and leakage reactance, the stator voltage can be written as V equal to F E upon F rated, B peak upon B rated into V rated. So, where V is the amplitude of the armature winding, F is the operating frequency, P is the peak flux density, F rated, B rated and V rated are the corresponding rated values. So, you can call it speed of induction motor can be precisely controlled by frequency control and can be made independent of variation in supply voltage, field current and load. So, therefore, keeping a V equal to V rated can be written B rated frequency F rated upon F E into V rated. This demonstrates the constant voltage variable frequency operation. So, in this mode machine operation is in saturation at rated voltage, and the frequency and any reduction in frequency will lead to the further increase in flux density. So, higher flux density will result in increased core loss and higher machine current. So, therefore, frequency less than the equal to rated frequency, the machine is operated constant flux density. So, BP equal to V rated, and this makes the equation V equal to F E upon F rated into V rated, and or VA upon F equal to V rated upon F rated, and this is a constant voltage to frequency operation. It is typically maintained from rated frequency to the low frequency, at which armature resistance drop becomes significant component in the applied voltage. So, for frequency higher than the rated voltage at its rated value, the air gap flux density will drop because its rated value. Thus, to maintain the rated flux density, the voltage have to be increased, which may result in insulation failure. Therefore, frequency above the rated frequency, terminal voltage is kept at rated voltage. Assuming that the machine cooling is not affected by the rotary speed, the maximum permissible terminal current will remain constant at its rated value. Therefore, for the frequency below the rated frequency, the machine power will be proportional to F E into V rated I rated. So, these are the torque speed characteristic. Below rated frequency, you will find the maximum torque as V by F constant, maximum torque is constant, and above base frequency you are keeping voltage constant, but frequency you are increasing, so flux will reduce. That is why the peak torque also reduce. And these are of course can be in 4 quadrant operation, because in many cases you need the reversible drive like traction you apply, and you have a reasonable regeneration even in metro and your traction, and even in electric vehicle also. So, a lot of applications are there where active load are there, and we can get regeneration by reducing the frequency. You can call it of stator winding. So, it can work as a induction generator, by varying the frequency smoothly, so that it develop the regulated torque with the regulated current during the, but we always operate the motor in stable region. Only in these region we never go to peak torque even, because we operate not more than twice of the maximum torque even in the stable region, because in stable region if you have a twice of rated torque, you will have a twice of the rated current. So, current is also proportional to the, let us say, the torque only. If torque is double, current is also double, like similar to like a kind of a DC motor. So, this is the characteristic when you can call it in variable frequency motor. Up to rated speed you will get the constant torque. After that torque will reduce because flux is reduced, and power of course is proportional to here, because torque is constant. So, power will be proportional to speed into your torque, and above the power is constant because speed is increasing, torque is reducing like. So, now coming to rotor resistance control. By rotor resistance control you can of course modify the characteristic by increasing the rotor resistance. Peak torque remain the same, but it is shifted towards the x axis, and you can get a speed control even for given rated torque. You can reduce the speed by putting this way. So, it is applicable only for wound rotor machine only, because you can keep external resistance only wound rotor induction machine, and speed is decreasing and constant maximum torque, and the speed at which maximum torque changes, and disadvantage a large speed regulation and power loss in external resistance which reduces the efficiency. The best methods in supply voltage and supply frequency is varied to keep V by constant to maintain speed regulation and use the Polarized circuit for frequency and voltage control and constant maximum torque. The rotor resistance control of the speed of motor can be controlled by varying the rotor resistance and slip at which the maximum torque developed of induction motor is proportional to rotor resistance, and the value of maximum torque remains unchanged at any value of rotor resistance. This method of speed control has characteristics similar to those of DC shunt motor speed control using resistance in series with the armature, and this method suffers from low frequency at rated speed and poor speed regulation with respect to the change in torque. And this is, you can call it for rotor resistance control actional circuit. So, you can call it actional. If you bring on other side, this actional resistance also have to modify with your turns ratio. Now, the stator current will be V upon R2 plus R2 actional square plus X2, and torque will be 3 by 2 V square R2 plus R actional into 3 by S R2 plus R2 square plus X2 square. So, maximum torque will be R2 plus R X2. So, which equals to the backdown torque, that 3 by 2 0.5 V2 square X2 into T breakdown. And this is how the torque speed characteristic changes. I mean, stator is applied to constant voltage and frequency supply, and the rotor we are putting externally, and characteristic can be modified by putting external resistance toward this. So, the rotor resistance is varied statically by using a principle of chopper. It gives the stepless or smooth control of. It has the advantage of low cost, good power factor, high starting current, high torque to current ratio for a wide range of speed. However, it suffers with wastage of slip power in external resistance, and its main applications are drive requiring low initial cost and high torque to current ratio, such as low power evacuators, cranes, host like. And this is the method on the rotor. You can have a variable resistance by changing the duty cycle of this chopper. So, this effective resistance can be changed at the output of diode rectifier. We change the effective resistance in the rotor circuit, and that is the how the current really their current and voltage relation there, and how the characteristic get modified with the duty cycle also. And this control has many advantages: smooth lap control, fast response, less maintenance, longer life and compact size. This also have a added advantage of assured balance between the rotor phase current and the static. Rotor resistance control can be operated in closed loop to get fast transient response during starting and braking, and this quality makes it superior than the conventional rotor resistance control method, despite the disadvantage of requiring motor derating. Now, some of the most important considerations in selecting induction motor is efficiency, starting torque, pull out torque, power factor and starting current. Now, coming to the numericals, a starting first example, a 460 volt 25 horsepower 60 hertz 4 pole star connected motor has the following impedance in ohms per phase referred to stator circuit: R1 equal to 0.641 ohm, R2 equal to 0.33 ohm, X1 1.106 ohm, X2 equal to 0.464, Xm equal to 26.3 ohm. So, the total rotational losses are 1100 watt and are assumed to be constant, and the core loss is lumped with this rotational losses. So, for rotor slip of 2.2% at the rated voltage and rated frequency, find the speed, stator current, power factor, output power, air gap and output torque and efficiency. So, coming to here the solution, first we got the synchronous speed 120 f by p, that comes 1800, then rotor speed 1 minus s and synchronous speed comes 1760, and now we can go to the stator current. So, first we can find out Z2, that R2 by S plus JX2. So, we get this impedance here, then ZF, that 1 plus XM and Z2 in parallel. So, this we get 12.94 at the angle of 31.1 degree ohm, and then we get the total impedance equal to Z stator plus ZF, and putting this value we get 14.07 at the angle of 33.6 degree, and I1 will be 5 upon Z total. So, per phase voltage is 460 by root 3, that is motor is star connected, divided by the 14.07 at the angle of 33.6. So, it comes the current 18.88 at the angle of minus 33.6 degree, because minus sign is there. The power factor is always lagging in induction motor, and power factor PF is cos 33.6 degree, that is 0.833 lagging, and output power is now to find out output power. First we find out input power, that is root 3 VLIL cos theta, and putting the value we get 12,530 watt. Then PSL, that is stator couple of 3 I1 square R1, putting value it comes 685. Then air gap power P in minus this stator couple losses, putting value we get 11,845 watt. Then P converter 1 minus S PAG, putting a value it comes 11,585 watt, and P output P converter minus P friction losses, putting value it comes 10,485, and then the typically converting this output power in terms of a horsepower divided by 0.746 watt, so it comes 14.1 horsepower. And the air gap and output torque, so T internal will be PAG upon synchronous speed, putting value it comes 62.8 Newton meter, and T load will be P out upon omega m, so putting value it comes 56.9 Newton meter, and efficiency is P out upon P in, putting value it comes 83.7%. Like now coming to example 2, a 460 watt 25 horsepower 60 hertz 4 pole star connected wound rotor induction motor has the following impedance in ohms per phase referred to stator circuit. R1 is 0.641 ohm, R2 equal to 0.33 ohm, X1 equal to 1.106 ohm, X2 equal to 0.46 ohm, and Xm equal to say 26.3 ohm. What is the maximum torque of this motor, at what speed the speed and slip does it occur, and what is the starting torque of this motor? If the rotor resistance is double, what will be the speed at which the maximum torque now occur, and what is the new starting torque of the motor? So, now coming to typically V Thevenin, we get the V phi Xm upon under root R1 square plus X1 plus Xm square, putting the value it comes to 55.2 volt, and RTH, I mean putting the value of this, we get like a typically 0.59 ohm, and XTH equal to approximately X1, that is 1.106 ohm. So, now we can get ST max R2 upon RTH square plus XTH plus X2 square, the value it comes 0.198, and corresponding torque corresponding speed will be Nm 1 minus S as synchronous. So, it comes 1444 rpm, and torque at this speed T max will be putting 2 omegas 3 VTH square RTH under root RTH square plus XTH plus X2 square. So, putting the value it comes 229 Newton meter, and coming to starting torque can be found by equation putting S equal to 1. So, putting the value S here 1, we get 104 Newton meter, and now if we say rotor resistance is double, so slip is now earlier it was 1, now it is 0.396, and the speed will be corresponding to now 1 minus S into S synchronous. So, it comes 1084 in place of 144, and the maximum torque will be now T max, putting the value there it will be 229 Newton meter, and the starting torque now putting the value it comes 117 Newton meter. Now, coming to example 3rd, the following measurement were taken on a 5 HP 4 pole 208 3 phase 60 hertz star connected induction motor. So, we have a no load test, log rotor test, and DC test. The voltage is 208, that is rated voltage, and 35 volt for block rotor at 15 hertz, and DC voltage for DC test is 20 volt, current is 4 ampere, 12 ampere, 25 ampere, 3 phase power is 250 watt, 450 watt, and of course, in DC we do not measure the power. So, determine the full load per phase equivalent circuit parameter of the motor. So, we can say from the DC test the star connected motor, so major stator resistance will be your R1 equal to 1 by 2 20 by 20, so it comes 0.4 ohm, and no load test only on no load the power delivered to stator copper loss, iron loss, and friction windage loss. So, since the separate data are not, no separate data are taken to obtain friction windage loss. So, from a graph they will be incorporated in the core loss for the. So, P no load is 250 watt, and stator loss is 3 into 42 into 0.4, that is 19.2. So, iron plus friction will be 230.8 watt, and this is the 3 phase quantity. Therefore, real power dissipated in RC will be 76.9 watt per phase, or RC dash will be 76.9 divided by 4 square, so 4.8 ohm, and R1 plus RC will be 4.2 ohm. So, now no load impedance per phase will be your ZNL 208 divided by root 3 divided into 4, that is 30 ohm, and ZNL square equal to R1 square plus RC plus X1 plus Xm. So, from this we get the X1 plus Xm equal to 29.5. Now, coming to log rotor test, so real power is dissipated in stator and rotor resistance, hence R1 plus R2 square equal to 450 divided by 3 into 12 square. So, it comes 1.04 ohm, and R2 dash will be your 1.04 minus 0.4, that is 0.64, and ZLR equal to 35 divided by root 3 into 12, 1.68, and ZLR square R plus R1 plus R2 square plus X1 plus X2 square. So, now reactance at 60 hertz will be your 60 by 15, that is into 1.32, that is 5.28 ohm, and since it can be assumed that X1 equal to X2 dash, so each resistance is 2.6 ohm. So, from no load test X1 plus Xm is 29.8 and Xm is equal to 29.264. So, it comes 26.9 ohm. To replace Xm and RC by Xm RC, we calculate the admittance Xm series with RC. So, real part will correspond to 1 upon RC and imaginary part will be 1 Xm. So, y equal to 1 upon RC plus Jxm, putting 4.8 plus J is 26.9 and putting the value, it comes 6.42 minus J 36 and to 10 power minus 3 mho, and y will be again 1 upon RC, the same formula, it comes this value. So, RC from here taking inverse of 155 ohm, Xm will be putting value 27.676, and this is the total equivalent circuit with different value of stator resistance 0.5 ohm, stator leakage 2.64, rotor leakage also 2.64, rotor resistance 0.64 by S, and your RC is 155 and Xm is J is 27.76. Now, coming to example 4, the input power to the rotor circuit of 6 pole 60 hertz motor running at 1100 rpm is 5 kilowatt. What is the rotor copper loss? So, synchronous speed is here Ns equal to 120 by F, putting the values come 1200 rpm, and the slip for rotor is Ns upon Nr by S, it comes like for element 8.33%. The air gap, now the air gap power is the input power to the stator. So, P is equal to 5 kilowatt. So, power converted to electrical mechanical form is P converted 1 minus N in Pg, putting a value, it comes 4584 watt, and the rotor copper losses are the difference between the air gap and so P rotor copper loss Pag minus P converted, and putting the value, it comes 416 watt. And now, coming to typically numerical problem 5, a 2084 pole star connected wound rotor induction motor is at 30 horsepower. It equivalent circuit parameters are R1 equal to 0.1 ohm, R2 equal to 0.07 ohm, Xm 10 ohm, X1 0.21 ohm, X2 equal to 0.21 ohm, P mechanical 500 and P core 400. For a slip of 0.05, find the line current, stator copper losses, air gap power, power converted to electrical to mechanical, induced torque, load torque, overall machine efficiency, and motor speed in revolution per rpm and radian per second. So, this is the equivalent circuit parameter given here from the data, and then the easiest way to find the learned current to get the equivalent impedance ZF of the circuit. So, from here, and we can find out total impedance Xm in parallel with the Z2. So, we get the ZF here, and then we can call it like a typically Z1 plus ZF, IL equal to IL V per phase, putting a value, it comes 78 at the angle of minus 22.8 degree ampere, and the stator copper loss PSL equal to 3 I square R1, putting a value, it comes 1825 watt, and air gap power is 3 I2 square R2 by S, putting a typically 3 IA square RF. So, putting the value here, it comes to 24 kilowatt, and the power converted to electrical is 1 minus S into Pg, value, it comes 22.8 watt, and T internal will be Pg upon omega, putting the value, it comes 127.4 Newton meter, and the output power of this motor is P out P converted minus P mechanical P core, putting the value, it comes 21.9 kilowatt, and output is your speed will be Nr equal to 1 minus N to Ns, putting the value, it comes 1710 rpm, and now load torque P out upon omega, putting value, it comes 122.3 Newton meter, and overall efficiency P out upon Pn, putting the value, it comes like your 84.6%, and the motor speed in revolution per minute is 1710. The motor speed in radian per second will be your 17 rpm 2 pi upon or into 1 minute upon 60. So, it comes 179 radian per second. Now, coming to question example 4, for the motor in previous problem, what is the slip at pull out torque, what is the pull out. The slip at pull out torque is found calculating the Thevenin equivalent input circuit and load rotor power supply, and then using the test. So, this is the we are taking Thevenin equivalent here to find out VTH, and that is ZTH, and that is the total equivalent circuit. So, we got ZTH here, then VTH and ITH. So, VTH is 117.5 at the angle of 0.6 volt, and slip at pull out torque S max equal to R2 upon RTH square plus XTH plus X2 square, putting value, it comes 0.164, and the torque pull out torque T max is equal to, putting the value here in the relation, it comes 210 Newton meter. Now, coming to example 7, a DC test is performed on a 460 volt data connected 100 horsepower induction motor. If VDC 21, DC 72, what is the stator resistance? What is this two? If this armature is connected in delta, then the phase are connected in parallel, one phase in test in line. So, you can call it VDC IDC will be 2 by 3 R1. So, R1 will be 3 by 2 VDC upon IDC, that giving a value 3 by 2 21 upon 72, it comes 0.4 438 ohm. So, these are some unsolved problem, which you can solve in the similar manner, and these are the references from which we developed this lecture, and thank you very much.